chasing waterfall.
Welcome again to today's class. So today we shall look into another important topic in chemistry, that is chemical kinetics. Yes, from the word kinetics is derived from a Greek word kinesis. Kinesis. A Greek word kinesis, which means movement. Yes. And so when you come across to this word kinetics, what comes to your mind is movement. Okay? Now, unlike thermodynamics, which talk about the feasibility of a reaction, chemical kinetics, what it does is that it discusses rates of chemical reaction. Yes. And so rate equation, when you have rate equation to be equals to k a raised to the power of x, b raised to the power of y, where k is what? Rate constant. It means that when you add this x and this y, what you'll be getting is called the order of reaction. Order of what? Reaction. Take for instance, if you have r equals to k a raised to the power of half, b raised to the power of 3 over 2, you tell them that x plus y, that means 1 over 2 plus 3 over 2 will be giving you 4 over 2 equals to what? 2. We call it second order reaction equation. This means second order. Then when r is equals to k a raised to the power of this simple mean concentration. So when we have r equals to k, a raised to the power of maybe 0 and b raised to the power of 1, you will notice that your x plus y will be equals to 0 plus 1 equals to 1. That is first order. Yes. Then when you also have r equals to k bracket a raised to the power of, let's say, half, b raised to the power of minus half, you would tell them that x plus this will be equals to half plus half minus half plus half equals to 0. We'll call this 0 order. When you also have r equals to k a raised to the power of, let's say, 1, b raised to the power of minus half, you tell them that x plus y will be equals to 1 minus half equals to half. This is what we call half order. So in chemistry, we have many order reactions. And it's important for you to know from this example, we can see half order, 0 order, first order or 1 order, second order or 2 order reaction. Yes, but the one we'll be discussing in full details in this video is 0 order reaction, first order reaction, and second order reaction equation. We need to check out what are the intrinsic properties in this reaction equation just mentioned. Okay, so let's go into them one after the other. 0 order reaction. 0 order reaction. For the 0 order reaction, its equation is concentration of any time equals to initial concentration minus rate constant times what? Time. And so that is the equation for it. Okay, and so what we do here is we will check out a lot of things here. First thing we will check is the half-life. And the next thing we will check is shelf life. Very important. This is because at elementary level, we need to understand this life we talk about, half-life, shelf life. At higher level, we talk about all the types of half-life, biological half-life, effective half-life, and all have you. But at elementary level, we want to just talk about the physical half-life of this. Yes, we'll discuss them in details now. So if the one we are talking about is physical half-life, for instance, it means the time it will take that element to decay to its half physically, the time it will take that element to decay to its half physically, or the time it will take 50% of that element to decay physically. You get it? And so that is about physical half-life. Then when you talk about biological half-life means the time it will take 50% of that drug or of that substance taken into the body to get eliminated. The time it will take 50% or half of that substance being ingested into the body to get eliminated from the body. And when we talk about elimination, elimination simply means metabolism and excretion. So two things make up elimination. When you talk about elimination, so to speak, it means metabolism and excretion. So the time it will take 50% or half of that substance to get eliminated from the body is called biological half-life. But if it is not happening in the body, if it is happening physically, the time it will take 50% of that substance to get to decay to its to decay. The time it will take 50% of that substance to decay is called physical half-life. But if it's taking place inside the body, you call it biological half-life. That is the time it will take 50% of that substance to get eliminated from the body. So you have to take note of these points. Okay? Now we are taking the physical half-life first. So the time it takes 50% to what get eliminated or to get decayed is what we check. That means our C will be equal to 0.5 CO. 50% means 50 over 100, that is 0.5. You put it here. You'll be having 0.5 CO equals to CO minus KT, 50%. And so minusing, you now say this is 0.5 CO minus CO equals to minus KT. 50% means half, like 50 over 100. This minus this minus 0.5 CO equals to minus KT half. And so T half, which is the half-life of a zero order reaction, is minus 0.5 CO all over minus K, where the K is talking about K0 order. And so minus will cancel this, right? And it's giving you CO all over what? 2. And it's giving you 0.5 CO all over KO. Or CO all over what? 2 what? KO. Remember, this O we are putting to this K is telling you we are talking about zero order O. Okay? And so, what does this tell you? What does it tell you? It's telling you that half-life of zero order reaction is dependent on initial concentration. That is, the higher the initial concentration, the higher the half-life. Is dependent on what? Initial concentration. Is dependent on initial concentration. So half-life is dependent on initial concentration. Please note this key point. Then, what do we mean by zero order reaction? In zero order reaction, the implication is that K, the rate is equal to K raised to the power of what? 0. That is total x plus 1 is 0. That means rate of zero order reaction. In zero order reaction, the rate of each reaction is equal to the rate constant, each of the reactants or any of the reactants raised to the power of 0. Where the 0 is the overall order of that reaction, which is 0 we are talking about. In mathematics, anything raised to the power of 0 is said to be what? 1. And so that means there is no concentration. This means that R is equal to K. R is equal to the rate constant. The rate of that reaction is equal to what? The rate constant. That means it is independent of initial concentration. Now, please note these two words. In terms of half-life of a zero order is dependent on initial concentration. whereas rate of a zero order is independent on initial concentration. Independent on what? Initial concentration. Rate is independent on initial concentration. Half-life is dependent on initial concentration. Please be able to differentiate these two. Okay? Then, in this zero order reaction, we can present it in terms of what? Graph. Watch. Look at the zero order reaction. That means the graph of concentration against time. And so it will have a negative slope. Graph of concentration against what? Time. Look at the against time. When you plot the graph of concentration against time, the slope will be equal to what? K. It's negative. It will give you a negative slope. That is why you see here negative slope. Now the point at which it meets the concentration axis is what we call the initial concentration. So they can ask you to sketch a curve given concentration at a particular time and the time involved. And after plotting it, they will say deduce your initial what? Concentration. That means the point at which it meets your y-axis is your initial concentration. Okay? Please note this. Then for the shelf life means the time it will take the 10% of the initial concentration to get eliminated from the body. If we are talking about biological shelf life. Biological shelf life simply means the time it will take 10% of that what initial concentration to get eliminated, that is, get metabolized and excreted from the body. What do we mean? That's about biological. But about physical shelf life. Physical shelf life means the time it will take 10% of that initial concentration of that molecule or drug to be what? Eliminated from the body. What we mean by this is that shelf life is all about talking about expiry date. Yes. If they said a particular drug has expired, maybe it's to expire this month, so it has expired, right? And you check the drug. Let's say we are talking about vitamin C. That vitamin C, if they say it has expired, what it simply means is that 10% of its potency has been lost. That is about physical shelf life of vitamin C. So for physical shelf life of vitamin C, the implication is that 10% of its potency has been lost. That is 10% of the active ingredients in it has been lost. Yes. That means when you see someone after being told that this drug has expired, let's say vitamin C, and you see the person pick it and leak, don't blame that person. He has checked up something. He has checked if the physicochemical property of that drug has been affected. Let's say the color. If the color has not been affected, that is, the drug is stored in a good storage condition, that person might be tempted to take it and nothing will happen to him or her. The only thing is that it will only do 90% of the work, 10% will not be done. Yes, but it will not do any harm to that person. Yes, that is because the physicochemical property of that drug is not affected. But whether a drug has reached the expiry date or has not reached the expiry date, and you check the physicochemical property, let's say the color, it was white before and now it is now yellow or black, please run for your life. Don't take it, whether it has reached expiry date time or not. Let's say it has reached expiry date and the color changed from white to blue, red, yellow, black, any color that is no longer white, please never you take it. It means that it has reacted. The activation energy of that drug has been reached and reaction has taken place, so it is reacting already. Maybe produce a poisonous substance or product, and if it's a poisonous substance or product is produced, the implication is that it will be very harmful when you consume it. But if a particular drug has not reached expiry date and you bring it out, let's say it was white before and now it is yellow or black or any color, please don't say it has not reached expiry date so you will take it. Forget about what is written on it. Yes, forget about the expiry date written on it. The implication is that the storage condition where the drug was stored is not met. The storage condition the manufacturer asks you to store this drug is not met. Let's say it was asked to be stored in a cool, dry area and you left it in a hot area or condition. It will expire faster. Yes. Or maybe they say keep it is photosensitive, that you keep it away from light and you expose it to light, it will expire faster. And so, please, whether it has reached expiry date or has not reached, and the physicochemical property of it has been lost, maybe start producing odor, color change, please do not consume it. So that is more of the things chemical kinetics is talking about, the half-life and the shelf life of it. Let's go back to what we are talking about. We said for the shelf life, it means that the CT is equal to 0.9 CO, because 10 has been lost, 10% has been lost, remaining 90%, and 90% means 90 over 100, that is 0.9 CO. Okay, and so you bring it to this zero order equation. 0.9 CO equals to CO minus KT 0.9. This KT 0.9 telling you about the shelf life. This goes here. 0.9 CO minus CO equals to minus KT 0.9. Therefore, T 0.9 is equals to this minus this will be giving you minus 0.1 CO all over what? Minus K. There's 0. Now, the shelf life of a zero order reaction, or the expiry date of a zero order, can be calculated using this formula. T 0.9 equals to 0.1 times initial concentration all over the decay constant, or the rate constant. This rate constant all over it. Every molecule, every substance have its decay constant. So you plug it here. So we have been able to get the formula for half-life of a what? Zero order reaction. The one of rate of a zero order reaction, and we said the half-life of a zero order reaction is dependent on the initial concentration, and it's gotten from 0.5 CO over KO or CO over 2 KO, whichever one you want. This KO is telling you zero order, the rate constant of a zero watt order. Then we also talk about the rate, and we said that rate simply means for that zero order, it means that the total x plus y is 0. That means anything raised by 0 is 1. The r is equal to the rate constant. And then the implication is that the rate of a zero order reaction is independent on the initial concentration. There is no initial concentration here. Okay? We also said that about shelf life, that is what we call biological shelf life. The time it will take 10% of that word to get eliminated from the body. But when we talk about physical shelf life, we say the time it will take for 10% of that drug to get what? Eliminated. Or for the physical shelf life, we say it is time it will take 10% of that potency of the drug to get lost. That is about physical what? Shelf life. Okay? Now we also went ahead to see how to get it. That it means 10% has been lost. So 0.9 CO. I will be having CT will be replaced with 0.9 CO equal to CO minus K T 0.9. So this minus, it will give you minus 0.1 CO. Then we divide it by what? Minus K. So that we'll get the value of what? The shelf life. So that is for this. Okay, we want to go to first order reaction. Please, if you do not understand a particular point or particular thing we just said, please make use of the comment box below and ask your question. If you do understand it and enjoy the topic, please feel free to click like button and share to your friends and your classmates at the end of the watching. Okay, let's go to first order. Under first order, we say that its equation is ln C equals to ln CO minus KT. That is for what? First order. Yes. Let's see some examples of reactions which obey first order. Think of radioactivity. Radioactivity is one of the reactions that obey first order. Yes. Now, in first order, look at how the graph goes. The graph of what? Ln C against what? Time. And when you have a graph of ln C against time, here is negative, so it will give you a negative graph. A negative graph. And so look at it. A negative graph. Okay? And so what you do here is, you say the point at which you meet your y-axis is called ln CO. And the slope is called K. K1. That means once you finish plotting the graph, this point is called lane CO equal to what? X. Whatever you get here, you call it X. So lane CO equals to whatever you get. If they ask you to get your CO, you say CO equals to what? Exponential what? X. Exponential X. That is, remove this lane, put what? Exponential, and put X. So that is how to get your what? Your CO when you finish plotting. So you just use your scientific calculator. Once you press shift lane, it has packaged it this way. You now put what you got as the value, what you got from here. That is what will give you the value for CO. Okay, thank you. And we go further to now discuss the half-life and shelf life of a zero order. But before then, what does the rate talk about? The rate talk about K2, K1, a raised to power of what? 1. That means for first order, the total S plus Y will be 1. That means that the rate of a first order reaction R is dependent on what? Initial concentration. R is dependent on what? Initial concentration, CO. Yes, please note this. I've mentioned what you have to note here, because when we go into calculation or question solving, you will be able to note what we are talking about. Once you are done with this first order, we'll look into their units. Units of what? First order. Units of zero order. But we have seen that R is dependent on this. Let's go to their units. Units of order of reaction. Unit of order of reaction. Because if a question is asked and you do not know the formula you have to use, you can use the formula, you can deduce the formula you have to use from the unit. Okay, unit formula is equals to, we say concentration all over time times 1 all over concentration raised to power of what? N, where N is the order of reaction. Concentration, this concentration can be in mole per liter or mole per dm cube. So which one do we use? We use any one. Let's use mole per liter. This means mole for zero order, its unit is mole per liter divided by what? Time, times mole per liter divided by time times 1 over conc raised to power of 0. Anything raised to power of 0 is 1. Why are we writing 0? Any means order of reaction, and order of reaction is 0. So anything raised to power of 0 is 1. 1 over 1 is 1. That will be giving me this to be mole per liter. Change this division to what? Times 1 over time. Now, what is the unit of time? The unit of time can be in second, in minute, in hour. Okay, let's say the time is in seconds. All over seconds. So we will be having it mole per liter per what? Second. When everything comes up. Then for first order, as we said in the starting point of the video, we will be concentrating on zero order, second order. For first order, we say mole all over liter all over second. That is the time. Times what? 1 over conc raised to power of what? 1. Now, this is a concentration which we say is mole per liter, right? Yes. So we replace it with conc. Okay? This, we cancel this. That will be giving me 1 over second or per second. So when a unit of K is constant, when a unit of this K is this, know that we are talking about zero order. When a unit of this K is this or this, know we are talking about first order. Then when a unit of K is for second order, we say that it is concentration all over second. Remember, we said that concentration is mole per liter or mole per dm cube, okay? Times 1 over conc raised to power of, what is your n? Any second order is 2. So this we take care of one of this. That will be giving you 1 over sec and conc, and 1 conc remaining. So what is the unit? The unit of it is, for the concentration, let's sort it out. For the concentration, we say concentration is what? Mole per what? Liter. Are you getting it? And so what will happen now is that this L will come up. L, then this remain down. L mole per what? Second. Okay. So we now say the answer is what? L per mole per second. That is the unit of second order. What are we trying to say now? In this zero order, mole is not having power of -1, but here mole is. So how you can memorize it is that zero order and second order interchanges their powers in mole and liter. Mole will turn to per mole, while per liter will turn to liter. That is about it. So whenever you see any of these units, be able to deduce which order it for. We want to go into first order reaction. Afterwards, we go into the second order reaction. Let's see the equation for first order reaction. The equation goes this way: lane C at a particular time is equal to lane CO, that is initial concentration, minus K1T. Please, this lane you are seeing here is not same with logarithm. Note that lane is equal to 2.303 log in base 10. Okay, so lane and log are not the same, exactly the same. So putting this in terms of log, we say it is log CT equals to log CO minus K1T all over 2.303. Okay, we have been able to see their units, right? We have been able to see their units, the unit of this K, the unit of that rate constant for each of the reaction orders. That is the zero ohm, the first ohm, and the second ohm. Now, it's important to note that there are examples of reactions which undergo first order reaction equation. Example of it is radioactivity. That is the commonest one, radioactivity. And so have it in your mind as you watch the video. I'll be using this lane ohm. Yes. Now I want to go into the half-life of first order reaction. Half-life of first order reaction. Remember, we said the half-life are of two types in this level we are discussing. We want to discuss the physical half-life of a first order and the biological half-life. Physical half-life simply means the time it will take 50% of that molecule, that substance, that element to decay. Are you getting it? 50% of that molecule, that substance, that element to decay. Yes, you can put it this way: the time it will take a particular element to decay to its half. That is about physical half-life. It's taking place in a physical aspect. But when we talk about biological half-life, it means the time it will take 50% or half of the initial concentration of a drug, of any substance, putting into the body to get eliminated to its half. That means if I take a food, if this is a food or any substance, if I take into the body and I'm trying to get the half-life of it means biological half-life is what I'll be talking about at that case, because I put it into the body system. And so we say that the biological half-life of that food, that drug, whatever you ingested into the body, simply means the time it will take 50% of that initial concentration to get eliminated from the body. Remember the word eliminated. Elimination simply means metabolism and excretion. Please don't forget it. We now say that from here, we say that CT is equal to 0.5 CO. We are looking for the half-life. I will now put it here. lane 0.5 CO equals to what? Lane CO minus K1 T. This will come this side, lane 0.5 CO minus lane CO equals to minus K1 T. Yes. Now please don't just subtract. Apply subtraction law of logarithm, which says that when two lane or log are subtracting, take their common lane out, then divide what they have. This will cancel this, giving you minus K1 T. Now, if you press lane 0.5 in your calculator, that is lane, not log. Lane 0.5 in your calculator, you have minus 0.693 equals to minus K1 T. Okay? This K1 means you are talking about first order reaction constant. First order reaction constant. So, we now say that this is half. I'm talking about the half-life. So the half-life should be equal to minus to cancel minus 0.693 all over what? All over K1. Remember, this is half-life. That is, it's talking about time. So units will be seconds. Unit of any time, whether half-life of a zero order, half-life of a first order, half-life of a second order is in seconds. Okay? Please have it in your mind. But from here, what can we deduce from here? We can deduce that half-life of a first order do not have initial concentration the way the zero order one have initial concentration. This one does not have initial concentration. So the half-life is independent on what? Initial concentration, CO. Is independent on initial concentration, CO. Whereas rate of reaction of a first order is written this way, where this one is telling you the overall order of reaction. Rate of a first order reaction is, it goes this way: A raised to the power of 1 will still remain as A. That means the rate of first order is dependent on initial concentration. Please note this. Be able to differentiate it with the one of what? Zero order own. Okay? That is about first order reaction. Then this is for half-life of a first order. What about the shelf life of a first order? The shelf life of first order reactions goes this way, that C is equal to 0.9 CO. How did we get 0.9 CO? The implication is that 100% is the total. Now, when the 10% is lost, we are talking about shelf life. When 10% is lost, what will remain is 90 what percent. And 90% means 90 over 100 equal to 0.9. So the C amount remaining is equal to 0.9 CO. That is how we got 0.9. Do you get it? If you do not understand any point of this, you just use your comment box below. You are free to do that. Okay? If you wish to support the class, you can also click thanks icon and subscribe there so that we'll appreciate as well. Okay. Now, what we need to do again is, we now say, since we have seen CT to be this, we will say that here lane 0.9 CO equals to what? Lane CO minus KT 0.9. We are talking about shelf life. Shelf life of first order reaction. Remember, we say shelf life means the time it will take 10% of the drug potency to get lost. If you talk about physical own or in the body, shelf life, biological shelf life, the time it will take 10% of the drug taken into your body to get eliminated. And we have discussed it in full when we are talking about zero order own. So they still go together. Okay, from here we say that lane 0.9 CO minus lane CO is equals to what? Minus K T 0.9. Okay? Now, trying to complete it here, we said that applying subtraction law here, we said that it will be giving you lane bracket 0.9 CO all over CO equals to minus K T 0.9. This we cancel this. Lane 0.9 will be giving you minus 0.105 equals to minus K T 0.9. Therefore, T 0.9 is equals to minus we cancel minus 0.105 all over K. This is about shelf life of what? First order. It's important to note that first order goes this way. Look at the graph of it. It means you are plotting graph of length CT against what? Time. Okay? Graph of length CT against time. And it will give you a negative graph where here will be your what? Length CO. The intercept on the vertical axis will be your length CO. Then the slope will be called K. This negative you are seeing here is as a result of negative graph. So if the slope is positive, it means it didn't obey first order reaction equation. Okay? So after getting your length CO, if they ask you to get your initial concentration, tell them that initial concentration will be equals to anti-log. Anti-log means exponential. Let's put it well. Length CO, what I got here, let's say I call it x. CO will be equals to exponential x, because opposite of lane, antilog of lane is exponential, while antilog of log is antilog of log is 10 raised to power. So we use exponential. So you press your calculator, shift lane, it will package it this way, then write the value you have here. That will give you the initial concentration of it. So you also notice that the shelf life, whether biological or physical shelf life of any molecule we talk about, is independent on initial concentration, because there is no initial concentration here. Okay, so we are talking about the first order reaction. That is about first order reaction on. Please go through it. Have any question, use the comment box below and ask your question. We go to second order reaction equation. In second order reaction equation, we said its formula is this inverse of this concentration equals to inverse of initial concentration plus what? Plus K2T. Yes, can see it now. That means that it goes this way, that in this one, its graph have to go this way. Graph of negative of concentration at any particular time against what? Time. Are you getting it? You attach the unit. You attach the unit. Attach the unit. Okay. So when you plot the graph of this against time, your slope will be what? Positive. Positive, because look at it, positive. We call the slope K2. Where it meets your y-axis, you call it 1 over what? CO. So that means if your 1 over CO is equals to a particular number x, therefore your CO will be equals to 1 over x. That is how to get it. And when you get 1 over x, you attach the unit to it. Attach the unit, mole per liter, mole per dm cube, mole, attach the appropriate unit to it. Okay. One of the examples of reactions which obey second order reaction equation is saponification reaction. Yes, saponification reaction is a typical example of reactions that undergo second order what reaction. So have it in your mind. Now, for the half-life, you want to get the half-life of this. You say your CT is equals to what? 0.5 CO. You put it here. 1 over 0.5 CO equals to 1 over CO plus K2T 0.5. That's for the half-life. Okay? Then what you do is you bring this here, 1 over 0.5 CO minus 1 over CO equals to K2T 0.5. This 0.5 means we are talking about the half-life, okay? LCM will be what? 0.5 CO. This divide this 1 times this 1 minus this divide this 0.5 equals to K2T 0.5. Okay? So what we now do here is that it implies that 1 minus this 0.5, sorry, all over 0.5 CO is equals to K2T 0.5. Okay? 1 minus this gave you this. So this cancel this. Therefore, T 0.5 is equals to 1 all over CO K2. Can you see something here? The half-life of a second order reaction is dependent on the initial concentration. How? Inversely proportional. Why? This CO is at the denominator. That means the higher the initial concentration, the lower the half-life. The higher the initial concentration, the lower the half-life. That means half-life, which is still what? 0.5 or T half, is inversely proportional to initial concentration. So it's still dependent, but in an inversely proportional way. Remember, the half-life is 8 seconds. Okay? Is an inversely proportional way. Then next thing we do here is we go for the one on shelf life. We said the one on shelf life is CT equals to 0.9 CO. Okay? That means the time it will take for what? 10% of the initial concentration to be lost. We bring it into the formula. 1 over 0.9 CO equals to 1 over what? CO plus what? K2T. Okay? Then we now look for the LCM. LCM will be what? 0.9 CO. 0.9 CO divided 0.9 CO. 1 times 1. Turning this to the other side, we have 1 over 0.9 CO minus 1 over CO equal to K2T 0.9. So look for their LCM to give 0.9 CO. 0.9 CO divided 0.1. 1 times 1. 1 minus CO divides 0.9 CO. It will leave you 0.9 equals to what? K2T 0.9. Okay? Therefore, T 0.9 is equals to 1 minus this 0.1. 0.1. Okay? All over 0.9 CO equals to K2T 0.9. So what we are having now is that this will be giving you this. So what you do here is we say look for LCM. We now say this divide this 1 minus this divide this 0.9. So it gives 0.1 over 0.9 CO equal to K2T 0.9. Now what you do, your T 0.9 is equals to your T 0.9 is equals to 0.1 over 0.9 will give you 1 over 9. 1 over 9, right? 1 over 9. So will give you 1 over 9 CO get 2. So I've made T 0.9 subject of formula. So this is the shelf life formula for what? Second what? Order. The shelf life formula for second order. 1 over 0.9 will be giving you about 0.11. 0.11. That is 9 divided by 1, 0.19. So that means that T 0.9 is equal to 0.11 all over what? CO get 2. So either you use this or you use this equivalent. T 0.9, that the shelf life is equal to 0.11 over CO get 2. CO get 2. Okay? CO K2, CO means initial concentration, K2 means second order rate constant. So the second order rate constant will be given to you, initial concentration will be given to you, you just compute it with your calculator and you get your answer. Now it's important to also note that the shelf life, which is 0.9, is dependent on initial concentration by inverse proportional way. That means the higher the initial concentration, the lower the shelf life. So have it in your mind as you go about this. We will see some questions on this topic, but before then we want to talk about Arrhenius equation. Okay, we want to talk about Arrhenius equation. Arrhenius equation has this formula that says that K is equals to A exponential minus EA all over RT. K equals to A exponential minus EA over RT, where EA is called activation energy, right? The K is the rate constant, R universal gas constant, T temperature. And so as this R unit is joule per mole per Kelvin, this T will also be per Kelvin. Are you getting it? It's equivalent to, the R is equivalent to 8.314 joule per mole per Kelvin. Okay, so T is also per Kelvin as well. And so from this equation, applying lane, because exponential is there, opposite of exponential is lane. Applying lane, we'll be having that lane K equals to lane A minus EA all over RT. That is what you'll be getting. Lane K equals to lane A minus activation energy all over RT. Now, what is this trying to tell you? It tells you that when you plot the graph of lane K against theta, temperature in Kelvin, when you plot the graph of this against this will be negative. You'll be having a negative graph. This should be negative. The slope will be negative, and the slope is equal to EA over what? R. The slope is equal to EA over what? R. It should be negative. Are you getting it? And so, whichever direction this graph goes, it must be a negative graph. And not only that, the intercept at any point on the vertical axis will be called your lane what? A. Okay? The intercept will be lane A. Then the slope will be activation energy all over what? The R. So you have to note this. Okay? So the way your graph will look like depends on your unit or the values you have. So when you plot it and you didn't get negative answer as your slope, that is where an issue will come in. The slope must be negative. That is why it's moving in a negative way. Then it's also when you have different rate constants, you now say that lane K1 is equals to ln A minus all over RT1. Okay? Then the second one should be ln K2 equals to ln A minus EA all over RT2. That means the rate constant and the temperature are where the variation come in. Okay? From here, this is called the frequency factor. The A is called the frequency factor. And so if you make ln A subject of formula, since it doesn't vary, and carry the other one to the other side, you now say that ln K1 plus EA over RT is equals to ln A. That is for the first one. Then ln K2 plus EA all over RT is equals to ln A. This is for K1 and this is for 2. So this is what we got from this and this is what we got from this. Since this is ln A and this is ln A, we equate the two. It gives you that, it will give you that this implies that ln K1 plus EA all over RT1 is equals to ln K2 plus EA all over RT2. Are you getting it? Where we say EA means activation energy. That means the minimum energy barrier that must be overcome before a reaction will take place in a particular substance. Okay? Okay. And so from here we have it that if this go this side, ln K1 minus ln K2, this will now go this side. EA over RT1, okay, RT2 minus EA over RT1. So this go here and this go here, right? You can say this come here and this come here depending. Okay, so what we'll be having, take logarithm law here, we'll be having ln bracket what? K1 over K2 equals to what? Look for LCM. LCM, this will give you EA over R bracket 1 over T2 minus 1 over T1. Okay, can you see it? And so LCM T2 minus T2, LCM will be T2 T1. So this divide is T1, T1 times is T1 minus this divide is T2 times is T2 what? 2. Okay, so here will be negative, and we now say this other one is what? EA all over what? R equals to what? Ln bracket K1 over K2. Okay, and so that is about this. If you take it this way, that this should go here while this should go here, the implication is that you will have here to be T2 and have here to be what? T1. Here will not be negative because this minus, so you have here to be what? T2 and have here to be what? T1. The reason why I interchange them is by taking this to this side and take this to this side and take this to this side. The reason why I did so is there is need for you to have a positive answer. Okay, there is need for you to have a positive answer, and so instead of you to waste your time after getting negative, you start dividing. It is better you use the one that will give you a positive answer straight away. So we now say ln K2 over K1 is equal to activation energy all over Rasa gas constant, all bracket 1 over what? T2 minus 1 over T1, 1 over T1 minus 1 over T2. That is because we carry this now. We carry this to this side, then carry this to this side. So once you are carrying this to this side, K2 will be up, K1 will be down. And this one going this side, T1 will be first, while T2 will be second. So T1, T2. The reason why we are doing this way is to see that whatever you get here is positive and whatever you get here is positive, and before you know what happened, you get your final answer. Now this formula is used to find one of the unknown variable here, maybe activation energy, maybe the temperature, maybe the rate constant, one of the rate constant, depending. Okay, so you use it to what? Find it. That is about Arrhenius equation. Note about the graph that the graph will have a negative slope, and the negative slope is equivalent to EA over R. Negative means the graph will cut negative. Then intercept of the vertical axis is called lane A, that is frequency factor. And the A, if you have gotten a value and you say A is equal to the value you got here, A will be equal to exponential that value, so that you can get the exact value of A. That is about this Arrhenius equation. Okay, let's see how to solve some problems on chemical kinetics we have on the board. Note that the Arrhenius equation, that equation we mentioned in one of our videos or in the beginning part of this topic, the equation is a graph of Linke against inverse of temperature. It's a graph of Linke against inverse of temperature. Okay, note it, have it in your mind. We have discussed it before now. Graph of Linke against inverse of temperature. Okay, let's go to the first question we have. The initial concentration of N2O5 in the following first order reaction was this. So this is the initial, our CO at this. The concentration of this after 60 minutes. So 60 minutes is telling you time. After 60 minutes was this. This is our normal C. Calculate the rate constant of the reaction at this. Wow. The initial concentration of this following first order. So because they say following first order, we will recall that lane C is equals to lane CO minus KT. Okay? Then what is our C? Our C is 0.2. Say now, packaging lane 0.2 times 10 raised power minus 2. Is it my, when this come this side, it becomes minus what? Lane what? 1.24 times 10 raised power of minus 2. We say is equal to minus KT. And what is our K? Did they give us our K? No, we are looking for the K. They say find the what? Rate constant. But they gave us the time, 60 minutes. And so what will happen is that we now tell them that our K will be equals to this, our K will be equals to lane bracket 0.2 times 10 raised power minus 2 minus lane 1.24 times 10 raised power of minus 2 all over minus 60. Carry minus 60, go the other side. Now you use your calculator. In your calculator is your scientific calculator. You see lane there. You say lane, so you package it this way. I package my own. This will be giving you a negative answer. Okay, and so divided by negative 60, our K will be equals to 0.0304 per minute. So use your calculator and confirm it, and comment on the comment box below so that you verify this answer. Now we go to question number 2, which says a reaction is found to have a rate constant of K equals to this. Find the half-life of the reaction. As we discussed before now, we have many formula for half-life of what? Reaction. Half-life of zero order, first order, and second order. So which one should we use? We do not know. So what you do is that check the value of K. What unit is it? Look at K is equal to this per second. Per second means it's talking about first order, because we say in first order the half-life, in first order the K, the unit of your K, which you call rate constant, is equal to per second. That is the unit of what? K. And we now say since it is in per second, that means watch that half-life we will use, it will be half-life of first order, which is 0.693 all over K. And what will it give you? 0.693 all over 5.5 times 10 raised to the power of minus 14. Okay? 0.693 all over 5.5 times 10 raised to the power minus what? 14 per second. Remember, the unit of half-life is second, but here the K unit will be per second. Are you getting it? And when you do this, it will be giving you, therefore, K half-life should be equals to 1.26 times 10 raised to the power of 13 seconds. You get? Because here is per second, so the unit of this one should be in second. 1.26 times. So just use your calculator well, use your scientific calculator well, and you will verify this answer. As you verify it, use the comment box below to tell me yes or no. For question number 3, a first order reaction has a rate constant of this per second. How long will 5 grams of this reactant take to reduce to 3 grams? To reduce to, so this is the final concentration and this is the initial what? Concentration. So we go to the formula that says ln C, because they say per second, that is first order, is equal to ln CO minus what? Kt. Our CT is 3, ln 3 equals to ln what? 5 minus what? What is your K? The K is given to us as 1.15 times 10 raised to the power minus 3 what? T. So we are looking for the time it will take to reduce to this 3. And so from here, we say take this to the other side. We'll be having ln 3 minus ln 5 all over minus 1.15 times 10 raised to the power minus 3 equals to what? T. So you package this inside calculator. Remember, ln is not the same thing with logarithm. So ln is what you will use, not logarithm place. You package inside calculator to get your time. What you'll be getting your time is, your time it will take the 5 gram to reduce to 3 gram will be 444.2 seconds. Seconds because the rate constant is in per second. If the rate constant is per minute, you put minute. If it's in hour, you put hour. If they ask you to convert seconds to minutes, you divide this second by 60. When you divide this second by 60, you are getting it in minutes. When you want to get it to what? Hours. You divide it by 444.2 all over 60 will give you the answer in minutes. Then 444.2 all over 3,600 will give it to you in hours. So whichever one they want you answer to be, please package it well. We go to the last question. So in the last question, it said the first order rate constant for the decomposition of earth iodide by the reaction days at 600 Kelvin is this. Its activation energy is 209 kilojoule per mole. Calculate the rate constant of the reaction at this. Remember, R is joules mole per liter per Kelvin. Okay? And so what we do is that we'll recall Arrhenius equation, which says that K is equals to A exponential minus EA over RT. And from here, this is when only one rate constant is given to you. Only one rate constant is given to you. But when more than one rate constant are given to you, you said that it is ln K2 minus ln K1 equals to EA over R bracket T2 minus T1 all over T1 times T2. And so they are giving you the parameters. So what we will be doing, we'll package ln K2 is what I'm looking for, equals to what? EA over R bracket T2 minus T1 all over T1 times T2 plus ln K1. Okay? What is our EA? EA 209 kilojoules, that is 209,000 joule per mole. So we now say that ln K2 will be equals to 209,000 all over 8.314. This R is constant, universal gas constant. Now, this is your final temperature, which you are looking for, and this is the initial temperature. So it says 700 minus 600 all over 600 times 700. Okay? 700 minus 600, 100 over 42, 420,000, right? So lane get to will be equals to 209,000 all over 8.314 bracket 100 all over 4 to 420,000. There. So this will require you making use of calculator. Yes, it will require you making use of calculator. Then plus lane what? K1. What is your K1? Your K1 is 1.6 times 10 raised to the power of minus 5. Okay? So plus, if you check lane of 1.6 times 10 raised to the power minus 5, it will be giving you minus 11.0. It will be giving you minus 11.043. To be giving you minus 11.043. Are you getting it? And so, if you compute this, please use your calculator to compute it. This times this divided by this. What it will be giving you is that lane K2 is equals to, you compute this, it will be giving you 5.9853. 5.9853. So you combine it with this 11.043. It will be giving you that lane K2 is equals to, if you subtract this, it will be giving you 5.0577 minus 5.0577. Just confirm it with your calculator. Okay. Then, since our lane K2 is this, lane, what is your K? K2 will be equal to exponential, because you are dealing with lane, you use exponential, minus 5.0577. Okay? K2 equals to exponential raised to the power of minus 5.0577. And that will be giving you 6.06. 6.36, please, not 6.36 times 10 raised to the power of minus 3 per second. 6.36 times 10 raised to the power minus 3 per second. That is the value for this question. So the final rate constant will be 6.36 times 10 raised to the power of minus 3 per second. Thank you guys for watching today's video. Please feel free to click like if you enjoyed the video, share with your friends, comment as well, turn your notification button for more videos that will upload. Thank you. See you next time.